What's up, guys? In this video I'll be covering three very famous large language model papers, and all of them have in common that they've publicly shared both the code as well as the weights. So the idea will be to kind of show you some of the connections, the commonalities between them. We'll not be digging into the actual technical details that much because it's basically just a transformer architecture, and I already assume most of you know how transformers work. If you don't know, you can check out my video I've covered a long time ago on how transformers work. But before we go there, this video is sponsored by Weights and Biases. Weights and Biases is an amazing machine learning platform that helps you track your experiments, do dataset versioning, and model management. You can see how easy it is to get started with Weights and Biases. They are framework agnostic, so that means you can either pick PyTorch, Keras, or whatever you want, and it's only a couple of lines of code. So you import the Weights and Biases after installing it by doing pip install, and then after you initialize the project here, it will start automatically logging both the configs as well as various system metrics such as GPU utilization, etc., etc. And if you instruct it to do so, you can obviously log curves, images, videos, and much more. Here's an example of a run that I want to show you quickly that's very representative. So here are some of the system metrics we're logging, such as GPU temperature, memory allocation, etc. If you instruct it to do so, you can log obviously losses, validation losses, accuracy, whatever you want. And finally, in this example here, you can see a hyperparameter sweep optimization experiment where we can, for example, select those runs that have very low loss, and then we can draw some conclusions, such as we can see here that higher epochs tend to perform best, and then lower learning rate tends to help, etc., etc. You can additionally log videos, not only images, and even more structured information and data such as tables. And here you can see this is not just like your dummy UI. You can apply various filters, such as, for example, show me those rows where the ground truth equals the actual guess. So that's our prediction, and after you click apply here, you'll literally see filtered out exactly those data points. So very cool. Finally, one of the features I really love, and there are many more features I won't show you here, but like creating super rich media reports such as this one, you can see how interactive it can be and how beautiful, and you can make it as complex as you want, as you can see here, with many cells in the grid and animations, etc., etc. Weights and Biases are free for personal use and academics, so check out the link down below to support this channel. And now let's get back into the video. So let's see which papers I'm covering. So the first one is what language model to train if you have 1 million GPU hours, coming from the BigScience event, and they managed to train a 176 billion parameter large language model, which is huge. That's the biggest currently open sourced LLM. Then we have the OPT model from Meta, so open pre-trained transformer language models, which was 175 billion parameters. And here I'll mostly focus on some of the struggles they were experiencing. We'll see those a bit later. And finally, the third paper will be GPT-NeoX-20B, an open source autoregressive language model from the Eleutherii community. Okay, so before we go there, let me kind of quickly show you the glimpse of what we'll see. So I'll be walking you through some of the chronicles that OPT folks as well as the Bloom folks shared. So here is one very interesting diagram where you can see on the y-axis you see the perplexity of the language model, so basically the loss, and you can see the part I want you to focus on is on the gaps here. And so you can see that like in this duration of like a month or something, they had these huge gaps where the model could not train because of either hardware failure or software bugs or whatnot. You can also see a bunch of spikes. You can see how these are kind of almost don't like form like a smooth curve, and that's because they were oftentimes they had to obviously start from a previous checkpoint. And so there was a lot of struggle in there. Just looking at this graph, it's kind of clear. And one interesting detail here as well is like the cluster deletion. So their cloud provider managed to delete their cluster in the middle of the run. And so yeah, those are some of the interesting nuggets we'll see a bit later. Okay, having said that, let's get back to the papers. I'm gonna quickly go through all of those. The reason I'm covering these papers is because over the next videos, I'll probably do a code walkthroughs of some of these projects. So stay tuned for that. So here I'm gonna give you some context and theoretical background. Okay, so first of all, we can see here that the Bloom folks come up with the same types of scaling laws here. So we have the loss on the y-axis and we have the compute in the petaflop days on the x-axis. And we can basically see the very similar curves to what Kaplan et al. From the scaling laws paper from OpenAI kind of already showed us. Petaflop days, by the way, stands for, so one petaflop day is sustaining one petaflop of compute for a whole day. So that many operations. Okay, so let me kind of go through here. This is going to be basically a recurring theme. All of these three papers literally took the inspiration from the GPT-3 model. So you can see here, they say we follow the architecture and hyperparameters of GPT-3 model. That's going to be like a commonality between all of these three papers. So let's continue here. They say we base this model size on Kaplan et al. So that's the scaling laws paper. However, after this paper was accepted for publication, but before it came out, Hoffman et al. Provided an alternative approach for selecting the model size. So that's the Chinchilla paper from DeepMind. I'm going to quickly just show you the graphs for those of you who are not familiar with the scaling laws paper. I strongly recommend you at least skim it. It's a very interesting finding, and it's also very empirical and very it's overfitted to a particular type of a transformer. So here you can see what the basic like postulate behind the scaling laws is if you can see on the x-axis, if we increase compute, so here on this left diagram here we have compute, and then we have data set size here, and finally we have number of parameters. So if you increase either three of those, you can see that the loss on the y-axis here, the test loss, is decreasing, and we don't see any sign of saturation here. So that was the paper that kind of showed us that we just need to scale the models and we'll get more and more performance. Now it's a completely different topic and problematic whether having a smaller loss like perplexity actually correlates with the metrics we actually care about, but that turns usually to be the case. But yeah, okay, so one thing that this paper, the scaling laws paper, showed is this one. So they say that the performance penalty depends predictably on the ratio. You can see this one here, meaning that every time we increase the model size 8x, we only need to increase the data, but roughly 5 times to avoid a penalty. So basically to avoid the overfitting. And so this is in stark contrast with the Chinchilla paper. So what they say here is that you basically need to increase the number of tokens of your training data set much slower according to this relationship you can see on the screen, according to this formula here, compared to the number of parameters. And then the Chinchilla paper actually showed a completely different finding, and that's that, so they say specifically given a 10x increase in computational budget, they suggest that the size of the model should increase 5.5. By they refer to the Kaplan paper, while the number of training tokens should only increase 1.8x. Instead, we find that the model size, so this is the important finding of this paper, the model size and the number of training tokens should be scaled in equal proportions. Okay, so the problem is there is no strong theoretical underpinning behind these, and like who knows how these laws will, and whether they will be valid for different configurations of transformers. If you change something, if you start using, I don't know, maybe alibi instead of relative positional encodings, maybe then the laws change, and we are not sure how sensitive they are. I might be wrong. Maybe the Chinchilla paper has like some stronger theoretical insights, but that's I'm recalling from my memory. Okay, so let's get back to the paper here. So the first thing they show is that obviously it's very important to have a high quality data set, and by high quality they mean like so having these diverse cross-domain high quality data such as the pile data set. So that's the data set that was basically collected by the Eleuther AI folks, and we'll see that their paper a bit later. And you can see that using the pile compared to these other data sets such as the Oscar or C4, gives them basically better accuracy on these various NLP tasks. You can see that the blue model here is on pair and even a bit better compared to the Eleuther's paper, the GPT-NeO paper. So that was the paper before this one, the GPT-NeoX-20B. And you can also see that basically the OpenAI's models do outperform them by some amount. So that's worth noticing. Okay, guys, so let's continue here. Let's see what else is interesting in this paper. So as I said, diverse cross-domain pre-training data combining web crawls with curated high-quality sources significantly proves zero-shot generalization over pre-trained datasets constructed from common crawl only. Okay, that's one finding. The second finding they had was that although learned positional embeddings outperform rotary embeddings, Alibi yields significant better results than all the other alternatives. Now this might be as well very specific to their particular set of hyperparameters in architecture. I wouldn't take anything fundamental out of this statement, but yeah, I'm just kind of walking you through some of the findings behind the papers. By the way, I did cover the Alibi paper, I think 8 months ago or something when it came out. So do check it out if you're curious to know more. And we'll see what the rotary embeddings, if you're not familiar, what those are a bit later in the GPT-NeoX paper. Okay, some of the other findings they had was they tried a bunch of different activation functions, and then they say here, we present our results in table 3, blah, blah, blah. Swiglu produces slightly better results than Delu. However, this comes at a cost of reducing the throughput by approximately a third. So I think they ultimately decided not to use it because of the throughput. Okay, so that's one more finding. And then they mention how and we already know this, basically it matters a lot where you put the layer normalization and how many layer normalization layers you include in your transformer blocks. And they say here, adding layer normalization after the embedding layer incurs a significant penalty on zero-shot generalization. But the thing is, when you scale the model up to very big sizes, then this thing helps stabilize the training. And when you're dealing with lower scales, in that case, you probably don't want to include it because you'll be sacrificing, as you can see here, the zero-shot generalization. Okay, guys, let's continue here. One thing that I kind of noted to myself as well, I was kind of, this is a curious finding. So they say, instead of manually writing, so this is about the multilingual basically evaluation, so trying to evaluate on multiple different human languages. And they say, instead of manually writing prompts for each language, which would obviously be very bothersome, we followed the strategy proposed by Lin et al. Using English prompts for non-English examples. This can be viewed as cross-lingual zero-shot generalization. They validated this strategy by demonstrating its ability to achieve zero-shot performance on pair with, and sometimes even better than, human-written language-specific prompts. This is kind of cool. So you literally take you have data sets with various different languages, and you always take the English prompt, and then you concatenate the answer in that different language. You repeat that a couple of times, and then you evaluate. And it's apparently the model learned to understand this, which kind of makes sense because you're training this joint a space of disjoint multilingual space when you're training the transformer on diverse data sets. And we always know that the machine translation kind of emerges as a consequence of this next token prediction if you give it enough big data sets with some presence of different languages. So, thing worth mentioning, and this is something we're probably all aware of at this point, and that's that the multilingual pre-training very significantly diminishes English zero-shot generalization. So the thing with this blue model is that they trained, this is a multilingual model, and because of that, it's not as strong on English as basically some of the other baselines. Okay, let's continue here. Couple of things worth mentioning. This is how they've chosen the final configuration of the Bloom 176 billion parameter model. So they reference here the scaling laws paper. It is notable that this Pareto optimal frontier describes very large models trained on few tokens. We call this training to optimality. So that's basically what I said before. Basically, you wanna, the scaling laws paper show that you wanna increase the parameters more than the number of tokens of your data set. And then they say this is in stark contrast with the common practice of training much smaller models on many more tokens to convergence. Okay. And now because they're training, they have a couple of arguments here, but one of them is that they're training on a multilingual data set, and because of that, they don't want to strictly follow the scaling laws, and so this is what they do. So we choose to use the optimality front as an upper bound on model size. So that's like the biggest model size will be determined by the scaling laws paper, and the lower bound on number of training tokens. So they'll probably have smaller model and more tokens, okay, compared to what the scaling laws paper suggests. The second very influential paper that had impact on the this like modeling decisions in this paper is this Levin et al. Paper. So they proposed a theoretically motivated and empirically backed law describing the optimal compromise between width and height. Width and depth, sorry. So for a GPT-3 size model with 175 billion parameters, they predict an ideal depth of 80 layers. Okay, so now it's just basically like combining Lego bricks. You have some constraints from the scaling laws paper, you have some constraints from this paper, and then given the compute they have, and that's roughly 1 million GPU hours on A100 machines, they decide on the hyperparameters of the model. So let's see what those are. So they use this many tokens, as you can see here, 70 to 80 layers because of this paper, and etc., etc. So finally, they end up with 3 best configurations, and the one they pick at the end is this one here. So they pick this one with 176 billion parameters, 70 layers, this many hidden dimensions, attention heads, dimensionality of attention heads. This is the memory footprint and the performance. Okay, so that's pretty much it. That's the first paper. Let me kind of show you these numbers side by side in the actual code base, and then we'll switch to the second paper. Okay guys, here it is. And as I said, I'll do a walkthrough of the code base. So basically, don't worry. I'll show you this code in much more depth later on. I just want to kind of briefly show you. So this is the BigScience workshop repo, and you can see the configuration for the 176 billion model. And you can see here the numbers are exactly what you see here in the table. So we have 176 layers. So you can see that somewhere here. Let me try. Nope, sorry, that's the number of parameters. So we have the 70 layers. So here is the variable for 70 layers. We have 14,336. You can see that number of hidden is exactly that. We have number of heads 112, etc., etc. So basically, yeah, this paper shows you how they've decided to pick the all of the hyperparameters of the model. Some of that was inspired by the GPT-3 paper, some of that was inspired by the scaling laws paper, and finally the Levin et al. Paper had an impact as well on the width and depth. Now I'm gonna quickly walk you through the chronicles they created. So basically, I'm gonna start here. So first of all, one more thing that's kind of common across all of the 3 papers is that all of them are using the NVIDIA Megatron library that helps you do model parallelism. Do check out my scaling, like ultimate guide to scaling video, where I cover a couple of these influential scaling papers, including Megatron. The second thing they all have in common is the deep speed library. Again, I did cover that one in my previous video, so do check it out. And the Bloom folks, because they had 384 GPUs at their disposal, basically decided to arrange those GPUs in this 3D fashion, so the so-called 3D parallelism, where one axis is basically pipeline parallelism, where you break the model such that you take a couple of first layers, you put them on one GPU, then you take the next n layers, you put them on the second one, etc., etc. Then you have the model parallelism, where you break the actual layers and then kind of take the weights of that layer and put one part on one GPU, the second part on the second one, etc., etc. And the third dimension is the data parallel dimension here, where you basically replicate your models across different GPUs, and then you feed them different portions of your input batch. Okay, Next up, I want to walk you through some of the chronicles they've shared. So there is this document called Lessons Learned. I link the repo down in the description so you can check it out. You can go. I strongly encourage you to go through, at least skim through all of these documents. I think it's a valuable learning experience. So a couple of things. So they have this title, How Training Divergences Were Overcome. So how they overcame the divergences. One of the methods was to just have a different initialization method, and it literally means so much. Like, I think they mentioned it somewhere. So it has made a huge difference to the training stability, and not only stability, but the final actual loss you converge to. And I remember back from my days when I trained the transformer model. So I had the original transformer implementation right here, and initialization, blah blah blah. I remember this diagram here. So here's what I said here. So initialization matters a lot for transformers. I initially thought that the other implementation using Xavier initialization is again one of those arbitrary heuristics, and that PyTorch's default init will do. I was wrong. You can see here 3 curves. These two are using PyTorch's default, and this one is using the Xavier initialization. So that was the moment for me when I realized how sensitive the models are to initialization and how vital that is. Okay, getting back to the lessons learned document here, embedding layer norms. So hopefully we're all aware of this. Basically, the position, whether it's before the residual connection or after, how many of them do you include, etc., etc. All of that matters a lot for the final stability. And finally, patience. So in some cases, so they say here, in some cases, in the case of a huge spike, it was taking 2K iterations for a training to return to the same loss it spiked from, and then it continued training as if nothing happened. So sometimes, in order to overcome the spike, you just have to wait. But more often than not, the training won't recover from a spike. Yet in other situations, the training diverts slowly without any spikes. Okay, so let me show you the spikes. So here is the, this is probably the most interesting chronicle I've seen. So the way they've trained the 104 billion parameter model. They had the most problems with this model, and then actually with the 176B model, the training was much more stable, and there are many reasons why that was. First of all, I guess they learned a lot during this whole trial, and then the second thing is, I think, like, they use bfloat, so the brain float format instead of the usual float 16, and all of that kind of brought the additional stability. So I just want to kind of quickly skim through some of the diagrams here. You can see that the problems they had with spikes. So during the training, the spike would appear and then the training would diverge. And they had a lot of experiments. They tried a bunch of things to try to kind of cope with those spikes, but they kept getting the spikes. They kept getting the spikes, like, throughout many experiments and many weeks. They couldn't get the model to converge. It was constantly diverging, and then I think only at the end did they start getting some better results after multiple months. I'll show you the 176B model a bit later. So let me show you one more thing. See here. So this is interesting. So they had 2 million backslash only samples in the dataset. So Hugh Nguyen, I don't know how to pronounce this surname, discovered that there are huge records with just backslashes in Oscar English version. So we set out to look at their occurrence. And so what happens when your model basically encounters this sequence, it can produce the spiking behavior, the divergence. So all of these details this is the messy reality of training large language models, and it's very nice that they've shared this. Okay, I did mention that the 176B was much more stable. They literally say here what makes the model so stable, and they compare. So here is the 104 billion parameter model. You can see a bunch of curves superpositioned here, and you can see the 176B. So it's literally like a smooth curve converging, and the loss is lowering as expected. So here is the kind of the overlapped image, and then they say it's a combination of probably a few of these improvements. It's kind of hard to pinpoint a particular thing, but I have a strong hunch that the bfloat format is what had a very significant impact here. So very clean data. They had better data set for the bigger model. They had the bfloat mixed precision regime, the FP32 accumulation for the pipeline, blah blah blah. Very low initialization, word embedding layer norm. but it was also used in, okay, so then I guess that doesn't explain it. Okay, that's pretty much it. They also have this document where they show how they decided to pick the parameters of the 3D parallelism. So basically how they decided on picking the tensor parallelism parameter, the pipeline parallelism, the data parallelism, all of those details. So you can kind of walk through this document at your own pace. It's too long for me to kind of extract any particular insight here, but that's pretty much it. Okay, guys. So now let's go to the second paper. I'm gonna open up the OPT paper, and let's start from the beginning here. So open pre-trained transformer language model. So these guys had a lot of problems training their models. Like reading through the logs was such a joy. So basically, let me kind of show you a couple of snippets from a huge document they have. Like there is like 140 pages or something of their logs, internal logs. So that's very cool. They shared those. So here are a couple of those. Once we identify the bad node, we need to document these lists of things to complain to CSP and get our money back. Give us our money back, you bastards. Okay, it looks like 26 tried to immediately upload the checkpoint and failed its CP commands. Then it took another step, lowered its scaler and tried uploading again. And again, the humanity. We're already at loss scale 0.25. And so on and so on. Like, oh hallelujah, things look good, but nope. Just kind of complete confusion. So I again encourage you to just kind of skim through the logbook. It's a very interesting read. Okay, let's start with this one. First of all, our models and hyperparameters largely follow Brown et al. So that's the GPT-3 paper. Again, with variations in batch size, mostly to obtain increased computational efficiency. So this is something I did mention in the previous paper as well. Whoops. So this is kind of a common thread for all of these three papers. They all follow the GPT-3 hyperparameters and advices. Next up, they say, we found that the pile was particularly full of duplicate documents and advise future researchers using the pile to perform additional deduplication processing. This is in particular relevant to the next paper I'll cover from Eleuther AI, because they did use pile and they did not deduplicate it because of the lack of resources. And they also, which is very interesting, they've done more than a single epoch, which is the common practice training LLMs. But we'll get there in a couple of minutes. A couple of interesting curves. Again, you can see iterations on the x-axis, learning rate on the y-axis. You can see that this was fairly ad hoc. Like basically the model would crash, they would retrieve the older checkpoint and then lower the learning rate such that in order to try to avoid the instabilities. And as a consequence of that, you get this piecewise weird graph here. Okay, you can also see the validation perplexity has a lot of these bumps, and it looks very funny. So here's the part that's joy to read. Basically, a lot of problems during the training. So the thing to mention in Meta's defense is that they literally had only a couple of months to do this. It was a very tight deadline, and so yeah, they didn't have the time to do this properly. But here is a couple of insights from the paper. So in total, hardware failures contributed to at least 35 manual restarts and the cycling of over 100 hosts over the course of 2 months. Given the difference between the number of hosts cycled out and the number of manual restarts, we estimate 70 plus automatic restarts due to hardware failures. I guess everything that can break will break, the Murphy's Law thing. Okay, we noticed a correlation between loss divergence, our dynamic loss scalar crashing to 0, and the L2 norm of the activations of the final layer spiking. These observations led us to pick restart points for which our dynamic loss scalar was still in a healthy state, so bigger or equal than 1, and after which our activation norms would trend downward instead of growing unboundedly. So this is just some detail about how they were handling the what was the heuristic they were using to pick the best checkpoint in order to avoid the future spikes. Okay, guys, let's continue here. So the results here, as you can see, on 14 NLP tasks averaged for the zero-shot evaluation, they are on pair with GPT. That's very cool. On the other side, for the multi-shot evaluation, where you do like 1 or 32 shots, you can see that the dashed line, the GPT model did outperform them on those tasks. So that means it's kind of better few-shot learner than the OPT model. And yeah, they say that the trend follows the GPT-3. That's what I said. So let's continue here. A couple of more interesting details. First of all, hate speech detection. They showed that the 175B model, the OPT model, considerably outperforms DaVinci in all settings. So that's very cool. And then you think about it, and this is always a double-edged sword. So if it's better at detection, that means it's probably more susceptible to generating toxic and hateful speech. So, and that's indeed the case. So let me show you that here. And they mention it. So overall, we see that OPT-175B has a higher toxicity rate than either Palm or DaVinci. DaVinci being the GPT-3 model. That's the code name. Okay, you can see here prompt toxicity probability of continuation. You can see that the blue curve, the OPT model, has the highest toxicity for across the whole axis here. Okay, guys. I think that's pretty much it. They kind of summarize saying that we still believe this technology is premature for commercial deployment. And yeah, I mean, understanding how these models work, just interpreting what's going on and why the model is outputting certain results, all of that, we are still in the early days. We're much better at getting raw numbers and benchmarks than knowing how to handle and align these models with human preferences. But that's a topic for a different video. I think that's pretty much it. That's the second paper. As I said, I'm just quickly giving you the overview here, and then in the next videos I'll be doing the codings series. Okay, yeah. Before this, let me show you the OPT logbook. So here's the big logbook I mentioned. This contains a bunch of notes that they were kind of accumulating throughout this period of a couple of months. I encourage you to check it out at your own pace. You can skim it. It literally took me maybe 20-30 minutes to skim through this and kind of extract some of the insights. Okay, so I did show you this diagram in the beginning of the video. So again, you can see the torture, the number of gaps here, and how many failures they were experiencing. So we saw the number 70 plus or something restarts. I don't want to count, but yeah, this might be at least in that range. Okay, finally, let's go to their final update. They have a couple of things, like some insights here. Let me pick a couple of them. So scaling to 1024 A100s to handle a real workload of this size is highly non-trivial. We will discuss infrastructure pain points below. Okay, ensuring training converges at this scale is also highly non-trivial without sufficient ablations at medium scale. Results obtained from training at small scale also do not necessarily hold when scaled up. We will cover these learnings in a note to be released in the upcoming weeks. Okay, so let me quickly read you the cluster deletion story. That's kind of funny. So given the holidays, we requested a pool of 12 buffer nodes to guard against hardware failures. 2 machines go down every day, on average. In the process of replenishing this pool, the cloud provider's support team accidentally deleted our entire cluster on December 21st. While the cluster was restored fairly quickly, it unfortunately came back with 60 machines that did not pass our infrastructure checks, etc., etc. So that's one of the interesting parts. Second interesting diagram here is this one. They showed that they didn't quite match the loss of the GPT-3 model, but we did see that on various NLP tasks, the zero-shot performance of the model did reach GPT-3. So that's again the discrepancy between like the loss value, the final loss value, and the actual performance might not always be that clear. Although we did see that we saw that the GPT-3 handles much better the few-shot prompts, and that might be because of lower loss here. Again, just a speculation, but that's usually the case. That's it, guys. Again, encourage you to go through it at your own pace. I'm going to continue on and explore the GPT-NeoX-20B paper. So, an open source autoregressive language model, and let's see what the insights here are. Okay, so we trained on a dataset that contains duplicated data for more than one epoch, but see no evidence of performance loss. While these authors claim that few-shot prompting doesn't improve performance on their task, we find that this is actually a phenomenon unique to GPT-3 and does not apply to either GPT-NeoX-20B or FairSec models. Okay, so that's just a note that it's dangerous to just take a single model and extrapolate from there because other models might have different behavior. So we'll see later in this paper that the probable explanation is basically dataset, the underlying dataset for that they use to train GPT-NeoX-20B, i.e. the pile, is of different quality and distribution compared to the datasets that were used for GPT-3. We don't even know what data was used, so yeah. Okay, so again, they mentioned here that they largely followed the GPT-3. So blah, blah, blah. The encoder model whose architecture largely follows that of GPT-3 with a few notable deviations described below. So that's again, the common thread that I mentioned multiple times. But this paper did have many more modifications compared to the previous ones we saw. Okay. Before this paper was published and the weights were released, they had a couple of iterations behind them. One of them was GPT-NeO, and the second one was GPT-J, which was basically supported by the Eleuther AI community, but executed by Ben Wang and Komatsuzaki. So that's kind of worth mentioning. So the architecture of this paper closely follows the GPT-J paper. So let's see what's the diff between those two, so the GPT-J and this one, compared to GPT-3. So first of all, they use rotary embeddings. I will not get into a lot of details how these work, but like here's your classical formulation of these attention. So you can see the formula here. We have the token here. We map it into the query. So this is going to be the query. We map this one into the key. Then we do the dot product. Blah blah blah, and then the rest of the notation is kind of weird because it's not summation. You want to have these scores in separate spatial locations. You don't want to sum them up. So this is kind of weird notation. I mean, looking at it, it's not even correct. Like you cannot just sum up these scores. It's kind of weird. Yeah, let me just make a div here. So the difference with the rotary embeddings is you have this matrix R here, which basically rotates your intermediate representation. So here's kind of the idea. So if you have a key or a query, so let's say we have a text here enhanced transformer with rotary position embeddings, and let's say that each of these words has a corresponding vector here. Let's say this is either a key or a query vector, and basically what they do is they kind of chunk this vector into d/2 groups. And that basically means that each of the groups is two-dimensional. And then, so once you have this chunk here, what you then do is you literally rotate it depending on its position and depending on the group index. So what I mean by that is, so this is group 1, group 2, group d/2. So because this is from group 1, you basically apply the θ1 angle, and because it's position 1, you apply m, and that's how you rotate. And then you get the output representation here, and that's the final representation here. So that's the modification that happens precisely here. Okay, guys. So that's one of the modifications they've used. The second one is this one. We compute the attention and feed forward layers in parallel and sum the results rather than running them in series. Okay, that's a fairly like a known technique for increasing the throughput. And basically does not sacrifice any of the performance. So they say here this led to a 15% throughput increase while having comparable loss curves with running them in series during early training. So I guess there is a minor penalty you're paying for getting the additional throughput. Okay. Then they mentioned, due to an oversight in our code, we unintentionally applied two independent layer norms instead of using a tied layer norm the way that these authors here do. So instead of computing this thing, you can see that they actually decouple ln1 and ln2. So just the bug they had in their code. Okay. Okay. They use here's the infrastructure they are using, and there is a nice diagram explaining how the setup looks like. The actual like node setup looks like this. So we trained GPT-NeoX-20B on 12 Supermicro servers, each with 8 NVIDIA A100 GPUs and configured with 2 CPUs. Okay, so here you can see the complex diagram. Even though it's a high-level diagram, it's still very complex. You can see how each of the 4 GPUs connects to a single CPU here, and then you have the different group here is connected with this CPU, And all of these here is what is commonly referred to as a node. So this thing here is called a node. You'll see this terminology a lot. Okay, guys. So again, a common thread. We opted to use the values from the GPT-3 paper to guide our choice of hyperparameters. To achieve a higher training throughput, we opt to use the same batch size as OpenAI's 175B model, approximately 3.15 million tokens. We extend AtomW with zero optimizer. So that's I kind of mentioned that because I did cover zero in my ultimate scaling guide video. I'll link that video somewhere in the description. So if you're curious to know more about zero, check it out. But the TLDR is, instead of replicating the model states and the residual states, so the gradients, the optimizer states, the weight, etc., instead of that, you just partition them, and that's how you achieve the zero redundancy. So that's what zero stands for. Finally, a note before we see the results. They say when comparing results in this work to GPT-3, the training data is almost certainly the biggest known unknown factor. Okay, and yeah, data is becoming the name of the game pretty much. A couple more differences they have compared to GPT-3 is the tokenizer. So we use a BP-based tokenizer similar to that used in GPT-2 with the same total vocab size of 50,000 with three major changes to the tokenizer. So first, we train a new BPE tokenizer based on the pile, which makes sense. You want to, because they're training on pile, they want to optimize the tokenizer for that particular data. Second, in contrast to the GPT-2 tokenizer, which treats tokenization as a start of a string as a non-space delimited token, the GPT-NeoX-20B tokenizer applies consistent space delimitation regardless. And third, our tokenizer contains tokens for repeated space tokens, all positive integer amounts of repeated spaces up to and including 24. Okay, this is kind of a mouthful, and just some idiosyncrasies of tokenizers. But like, let me show you like a graphical representation of what's going on. So here is the GPT-2 and how GPT-2 tokenizer would tokenize this piece of text, this snippet of code. And here is how GPT-NeoX-20B would tokenize that same text. So this is what I mentioned about the basically the spaces. So you can see that basically all of these spaces here are encoded as a single token. Similarly here, etc., up to 24. So literally until you get to 24, it's a single token. That's how I understood this part. Whereas on the other side, you can see that GPT-2 literally encodes each of these spaces as a separate token, and that kind of bloats the number of tokens to 55 here compared to 39 in this paper. Okay, guys. So I mentioned this a couple of times. We see no drop in test validation loss after crossing the 1 epoch boundary. Here are some of the diagrams they have. And it's a common practice to always train only for a single epoch. I guess partially because you have so much data that going for multiple epochs would be super compute intensive. So people almost never go to more than a single epoch. And there are some papers showing that the model starts memorizing very quickly if you start going multiple epochs. So people usually just do single epoch. In this paper, they literally continued training, and they didn't see any signs of validation loss starting to diverge or anything. So they just kind of continued. And yeah, I mean, I guess the common wisdoms should be questioned, because the wisdom is not based on any solid theoretical understanding of why this works. And like LLM, large language model training is pretty much like dark magic and alchemy, as many refer to it. And so I think it's completely legit to do something like this. If it's giving you better performance, why not? Okay, so let's continue and let's wrap up this paper. Let me show you the results they get. So this is the zero-shot performance of GPT-NeoX compared to GPT-J, FairSec, and OpenAI's models. You can see it's pretty much on pair with them, but then it really starts shining once you start using it on A mathematical data sets and like these arithmetic tasks, which is, I guess, partially because a huge part I mean, not a huge part, but like significant portions of Pile are like these scientific websites such as archive papers, etc., etc. So because of the data set, it seems that this model came much better compared to the other baselines. You can see the orange dashed lines here. It's kind of outperforming all of the other baselines. If I'm not wrong, I think their fuchsia performance, not only on these data sets, but in general, is also better compared to GPT models, but I don't see the diagrams here. So yeah, okay, this is actually the one I'm referring to. So this is the 5-shot evaluation. You can see that, again, GPT-NeoX is much better when you give it multiple shots. So it's kind of a better few-shot learner, apparently, compared to the GPT model and FairSec, etc. And final note here, we opted to choose hyperparameters based on a mixture of experiments at smaller scales and by interpolating parameters appropriate for our model size based on previously published work. But because I think however, several aspects of both our model architecture and training setup, including the data and the tokenizer, diverge significantly from GPT-3. As such, it is almost certainly the case that the hyperparams used for our model are no longer optimal and potentially never were. In the appendix, they go on to say and argument why it's a good idea to release the model weights, because back at the time when they released this model, this was the biggest model out there. Now we have Bloom, now we have Opt. But like, this was a very important contribution to the community and just a very valuable thing for like researchers and people who are not as well financed as some other research labs. And that's it, guys. So those are the 3 papers I wanted to cover. So again, GPT-NeoX-20B, Opt, and Bloom paper. So we saw a couple of commonalities between them. They were all following GPT-3's hyperparameters and recommendations. We saw that they were all using pretty much, except for the Opt paper, both the Deep Speed and Megatron, whereas Opt was using only the Megatron library to scale up these models and train them, which is a completely non-trivial thing to do. Most importantly, the value of these projects is that they've shared both the code as well as the process as well as the weights, which is a huge contribution to the community, so kudos for that. Guys, if you like this video, subscribe to this channel, share it out with your friends, and expect new coding videos coming up where I'll be walking you through some of the code bases behind these papers, so stay tuned for that, and until next time, bye bye.